Hello again, Dave here, and today I'd like to talk to you about power density. And I'm going to do this video a little bit differently. I started to write up a script and thought I'd watch it on my laptop and use it as a teleprompter, but then eye contact and direction and camera angles and everything wasn't. I'm still playing with it. But I've got the script on my smartboard, copied and pasted it over, so I hesitate to read it to you, but I think it is going to be clear and concise and hopefully cut down on the amount of time we spend with the video. Today I've got some helpers with me today. Some Lego pieces, and I've put a lamp together, and hopefully these guys will help me explain power density to you. So, last video we described work and what work is, and the idea that power is the rate at which work is done. Today we're going to look at power density, how power, distance, and area are all interrelated. And I'd like to suggest the idea of power density here applies to birthday cake candles, campfires, incandescent light bulbs, speakers, any sort of radio with an antenna. I've got a walkie-talkie here. This happens to be for amateur radio use, but basically any sort of transmitter with an antenna. My Wi-Fi router's hiding around behind the Lego at the moment. Cell phones, cell towers, TV stations, anything else where power spreads out, whether in the form of heat or light or sound or radio signal. So let's start with this demonstration, and after that we'll get into some math. So, let's do this. So I've got a 60 watt light bulb here and some Lego base plates. Each of these plates is 10 inches. Get my tape measure out here. 10 inches or 25 centimeters square. So essentially a quarter of a meter long, quarter of a meter wide. And I've arranged these in a sort of a cube, and I want you to keep this cube idea in mind. So if I had 6 plates covering all 6 sides and the light bulb inside, I'd have top, bottom, front, back, left, and right. I've got my Star Wars minifigures there as a homage to yesterday's May the 4th. And I've got a nice decorative light bulb. It might be a little hard to see once I turn it on, but there's like this really cool coil sort of filament inside. Canadian Tire. It costs a little money, but nice and gives a little ambiance or aesthetic or a steampunk sort of look. Anyhow. So if I've got this 60 watt light bulb, and once I turn it on, 60 watts of electricity coming in through the cable, 60 watts of, I'm going to guess 40 watts is going to be heat and 20 watts is going to be light, but let's pretend it's all light for now. So I've got 60 watts of light spreading outwards in every direction equally. 60 watts, 10 of it's going to appear there, 10 of it's going to shine down, 10, 10, 10, 10. 10 on each plate, grand total 60. So 60 watts divided by my 6 plates should give me 10 watts. Let's turn this on for full effect. There we go. That might be a little... We'll see if the camera cooperates. I think you can see the... Can't adjust my camera too much, unfortunately, but I think you get the general idea. So 10 watts on every plate. Now, let's make the cube twice as wide, twice as deep, and twice as tall. This is where extra Lego comes in handy. So I'm going to add another 3 plates to this side here. Hopefully that stays. And I'll back my camera up so you can see 4 plates. Now this time, instead of the light shining 10 watts on each of the 6 plates. Now you can imagine I've got 4, 4, 4, 4, 4 on every side. I'm going to have 24 plates total. And I just reposition the light bulb in the middle of this larger cube. I don't have all the plates I need. I don't have 24 plates. But the general idea here now is, now you can see the light shining on each of the plates, and it's not quite as intense. In fact, this is where the math comes in. We'll start building the math up here. So if I have 60 watts, the light bulb hasn't changed, the electricity coming in hasn't changed, but I've got 24 plates now. Each plate is going to get, well, I'm going to have 10 watts to this side, but I divide by the 4, I'm going to end up with 10 over 4 is 2¼ watts for each plate. So what have I done with my distance? From here to here, I'm now 1 plate away instead of half a plate away. So 1 plate away, I've doubled my distance. My power density has decreased by a factor of 4. So my box is twice as big in each direction. The lamp is twice as far from each plate. And my power has gone down by a factor of 4. So distance went up by 2. Power went down by 4. Let's turn this off. Get my Lego out of the way so I can see my smart board again. So, the key point with all this Lego, so set that aside and return to my regular method here. So the key point here is power density is inversely proportional to the distance squared. So every time I double my distance, my power goes down by a factor of 4. If I start at 1 meter away and I go 10 meters away, I square that, my power is going to go down by a factor of 100. So if you're driving past a radio station, for example, and you notice you're 100 meters away, and then you drive a grand total of a kilometer away, you've gone 10 times the distance, your power level a kilometer away is going to be 100 times smaller, 10 squared. This applies to cell phones too, by the way. Okay, let's go to next page. So observation here is light is brighter near the center of each side. Oh, I should show you that too. Can I do this? Let's see. That's probably a good position right there. So you'll notice it's really bright here, and then it tapers off towards the edge. Likewise, it's pretty bright here, and it tapers off downwards and outwards as well. So I'm using the math we're using right now is a square, and we need to improve that a little bit. We're going to replace the square idea with a sphere. So we'll do a little high school geometry review. Whoever thought you'd need surface area of a sphere? Well, here's where it comes into play. Glad you remembered it from so many years ago. Power density then is going to be the power in watts from my light bulb or my radio antenna divided by surface area of a sphere. In this case, 4 times pi times the radius squared. So just to give you a kind of ballpark, by the time sunlight reaches the surface of the Earth, say your parking lot or your green lawn in the summer, for 1 square meter, or about a yard by a yard, that area is going to receive close to 1,000 watts of power from the sun. We can harness that with solar power solar panels and solar-powered water heaters, etc. But just to put things in perspective, that's 1,000 watts per square meter. Now you might want to take protective measures in this summer. You might want to put some sunscreen on, or wear some sort of footwear so your feet don't get burnt at that level. But nevertheless, that's a typical amount of power for the sunlight. I want to get into safety code 6 here and compare that. So let's go over to Google. I'm going to put the link to this in the comments when I post the video. This is the Government of Canada's web page. This is Health Canada, and all you have to do is go to Google and type in Safety Code 6, Health Canada, and this will bring you to, you might have to click a link or two within Health Canada to get to this, because there's a few other documents discussing this, but this is the main document. Limits of human exposure for radio frequency electromagnetic energy, frequency range from 3 kilohertz to 300 gigahertz. This pretty much covers everything. There's a little table in this a little further down that I had bookmarked, so I'm going to jump to the table. This is section 2.2.2, electric field strength, magnetic field strength, and power density between 10 megahertz and 300 gigahertz. Once again, this covers most of the stuff, including all cell phones. So here's my table, and I'm going to draw your attention to the column that says power density, and these are for each of these entries is for a different frequency. You'll notice there's a value of 2 watts per square meter, there's a value of 1.29 per square meter, and there's a value of 10 watts per square meter, and 10 watts per square meter again, and then there's a couple equations in here. And what this does, I'll go back to my smartboard. And I'm going to insert a page here, and I'm going to draw a little graph for you. So if we label power density here, watts per square meter, and we label frequency here, and they do this kind of funny. They go up by powers of 10, so this is logarithmic, and they do the same over here. 10 meg, 100 meg, 1 gig, 10 gig, etc. It's supposed to be a G and not a K. Anyways, what those equations do is they say for a certain range, I forget what it is, the limit is 2, for another range it's 1.29, and then for another range it's 10. I'm not drawing this to scale. Where those equations come in is those equations basically draw lines like that. Let's say there's a tapering, or things ramp up or ramp down, as the case may be. But the most what are we going to say? The most strict is this one here, 1.29 watts per square meter. And this is for uncontrolled environments, and what we mean by that is somewhere the general public can be expected to happen upon. For controlled environments, working in a radio station, for example, where the people there are expected to know the hazards and the precautions and know where the on-off switch is and whether they're transmitting or not, these sorts of things, the limit can be higher so that we can work with them safely. But for the general public, uncontrolled environments, 1.29 watts per square meter. And I'm going to use this most strict number regardless of whether it applies to, we haven't talked about frequency yet, so regardless of whether it applies to frequency or not, we're going to go with the most strict definition and give you rough ideas of how that applies. Let's go back to my smartboard here. And next page. Actually, go back 2 pages. There we go. Okay, so last lesson I talked about the power from my wireless router, which is hiding behind the Lego here. I'll get this Lego out of the way. So this little guy, if you remember, was... so you can see what I'm talking about. So here's my wireless router, and if you remember, I said the antenna here was... well, there's heat coming off the case, there's light coming out of the front, there's electricity going out the wires to my printer, etc. But if, worst case scenario, none of those things delivered any power, and all the power came out here, we came up with the number of 7.65 watts. So I simply multiplied the volts listed on the bottom by the amps, and I got this number. Let's find out what a safe distance is for me to be exposed to this antenna, assuming all the power comes through the cable and out as radio waves. So I can use my power. I'm going to put my power in here, and I'm going to put my my safety limit, my power density that I'm allowed here, and I'm going to solve this equation now for R. So this is surface area of a sphere. We're going to rearrange this. I can divide both sides by 1.29, multiply both sides by 4 and pi, take the root of it all, and should come up with, let's do that, 7. I'm going to double check my numbers here in the calculator. Menu 1, 7.65 divided by 4, divided by pi, and divide by 1.29. And then we multiply both sides by r, and take the root, r squared I should say, root of all this, 686 millimeters. So yeah, math works out. So this is approximately 70 centimeters. Get my tape measure out here. And measure off 70 centimeters. So there's a safe distance from here to my finger. So 7 watts are coming out of that, and by the time that all dissipates to a safe level, we're sitting 70 centimeters, or about 2 feet 3 inches. 2 feet 3 inches away. I should also add that the frequency here is actually closer to the 10 range rather than the 1.29 range, so we can actually get closer based on the frequency, but we haven't discussed frequency yet. I can also get closer because not all the power is coming straight from here into the antenna. I would guess a fair bit of it is dissipating as heat simply by the electronics doing their job at calculating which packets of information go where. So that's that. That's the math behind this. Let's go to next slide. Safety Code 6, Health Canada Safety Code 6 averages things over 6 minutes. So I could spend some considerable time closer and then some considerable time farther, and if by average I end up at 70 centimeters, I'm well within my range. So this is the safety limit recommended by Health Canada. And you might think, well, what happens if I get too close too long? I'm going to use the analogy of driving a car. If you've ever exceeded the speed limit by 10 kilometers an hour or 6 miles an hour in the States, your chances are you didn't lose control of the car. Chances are nothing bad happened. Maybe you got a ticket, but typically there's a safety factor built in for speed limits. When civil engineers design the ramps to get on and off a highway and the banking angle and all that, and they post a speed limit, there's a considerable safety factor there. So you can exceed it. Not that I recommend this. I don't recommend breaking the law, but you can exceed some of these limits and still have plenty of room for safety error or safety margin. So if I get closer than 2 feet or 70 centimeters to this wireless router, I'm not overly concerned. Kind of like birthday candles on a cake or a campfire. You can get closer within reason. You get close enough, long enough, you'll get some heating is going to happen. Same thing goes with this sort of power through a router. Minuscule amounts. Practically speaking, and this is where I would recommend in practice, don't put this within 3 feet of your pillow on a bedside table. Leave it there while you're sleeping. Day in, day out, that's not something I'd recommend. This router happens to be in a bedroom. It's probably 2 meters away from the bed. I'm not overly concerned. So this is, if you want to err on the side of caution, the farther the better. If you're concerned about, if you want to maximize your reception within your property, probably the higher up. Don't put it in the basement. If you don't want your neighbors browsing your signal, maybe hiding the wireless router in the basement is the better idea. But generally speaking, keep it 3 feet or more away from your pillow when you're sleeping or anywhere else where you're operating much of the time. So that's today's lesson. I think that's it. That's all I had planned. Yep, that's it. So next time we'll look at frequency, and I'd like to start exploring where the frequency factors into safety code 6 and where that starts to affect cell phones and wireless and 5G and 5 gigahertz and what the difference is between all that. But I want to build up to that in terms of what a sine wave is, what a waveform is, what frequency is, how we measure it, what difference does it make, and got a few practical examples once again. So that's where I'm going with this, and then we'll get into generations of cell phone. What was the first generation like? What did it do? How did it work? What's the next one? I'm going to throw some AM and FM radio theory in there too along the way, but that's where I plan to go. Thanks for tuning in. Thanks for watching. Thanks for logging in, I guess, is the word now. And if you want to keep up to date with new videos, I'm sure there's a like and a subscribe button. So feel free to like, feel free to subscribe, feel free to sign up for alerts. And if you've got comments on how I can make these videos a little better, send me a private message through Facebook, or if you've got my email address or my phone number, feel free to do that too. Thanks for watching. Bye for now.